Good morning, everybody. Welcome to our webinar about compressed air monitoring, where there's no time to waste. My name is Pascal van Putten, and I will be both your host and presenter today. And with me is also Kuraa. I will just first explain you the program, so we'll go back to the presentation. Today, there will be two presentations. The first one by Kuraa from Enersize, who is going to talk about ISO 50001 and compressed air monitoring. And then there will be my presentation showing the benefits of compressed air monitoring and the three cases actually where I will show you why it's so important to measure flow in compressed air. After the presentations, there will be about 15 minutes for question and answers. And in your screen, you will see a chat window where you can enter those questions. And our moderator, Fanny, who is also with me today, will select the questions to be answered. If there's any lack of time, we will don't worry, because we will get back to your questions after the webinar in a private email. So let me introduce you Bo. Kuraa has many years of experience in energy optimization of industrial processes, cleaner production and systematic maintenance, including the implementation of energy management systems in accordance with ISO 50001. And he works for Unido worldwide, and he's now also with Enersize as Vice President Technical. So I will switch now to Bo for the first presentation.
Thank you very much, Pascal. Good morning, Europe, and good afternoon, Asia. So I think you can see my first slide. Yes. My name is Bo Kuraa. I'm Vice President Technical for a company called Enersize. It's a company with a headquarters in Finland, a research department in Sweden, and that offers measurement and data acquisition on compressed air system. The data acquisition is based on IoT and cloud computing, and the acquired data is analyzed in a way that provide an overview of energy saving potentials in a compressed air system. We have our own compressed air experts and saving action team who are responsible for making the savings happen, and by taking responsibility for the whole chain, so to say, from measurement to actually saved kilowatt hours, Enersize can guarantee you a successful project, both from a substantial financial upside and huge positive environmental impact. The offering is based on a revenue sharing model where Enersize covers the risk and including any needed investments that are necessary to achieve the savings, and the revenue can be achieved and shared between Enersize and the customer over maybe a 3 to 5 year contract, depending on what is agreed. I will give you a little overview of what I'm spent the next almost 20 minutes to talk about. I will say something about ISO 50001 and compressed air. ISO 50001 is the energy management standard. Next is how to change a company culture for energy savings, and I will finish with a case studies showing a short return of investments for compressed air savings. Let's take a look of what ISO 50000 is, energy management system. Basically, it is only a management system, and it should be implemented so it fits the size and activity level of the company. But it's one size fits all that will fit into any company. But of course, it has to be adjusted to the activity level and the energy consumption of the company. It is an important framework if you want to see improvements of the energy performance of the company. So I will very much recommend all companies to have a system like this, even if you cannot or do not want to have it certified. You can implement parts of it that can save you energy. As you can see in this box to the left, it is divided into different colors. The light blue is where the top management make the decision to implement the system. They develop the energy policy and provide the resources that is needed to operate a system like this. And they select a management representative to make sure the system is always connected to the top management. This is the only way this will happen, or this will work. It is the responsibility of the top management to implement such a system. And this is why there should be a strong connection between the top management and what is going on in the company. So commitment and roles and responsibilities belongs kind of the two first paragraphs belongs to the management to do. The yellow box, the planning box, is where you get an overview of the energy consumption of the company, the activities, what production equipment consume the most energy, and a lot of other information about the company that is needed later on. I will come back to that in more details on the next slide. But here we are talking significant energy users, energy performance indicators, opportunities list, and operational control. The green boxes in below is more about the day-to-day operation of the management system when it has been implemented, such as operational control in real, and checking performance indicators, control of energy consuming equipment, and implementation of opportunities. And this is where we save the energy. The system does not save energy itself. It's only when we work with the system, it will start to save energy. So the green boxes is where we really save energy. Let's skip to the next slide and focus more on the planning. And since we are talking about compressed air today, we should see this as from the compressed air point of view. You see the management review. I will just say a few more words about the management review, because when we have operated the system, let's say in half a year, we will need to report back to the top management, the so-called management review. This is where we report back what have been improved, how much we have improved, and if we need the top management to provide more resources to, let's say, get to the next level of energy efficient operation of the company, maybe investment in more advanced monitoring or control system. So this is the way we connect to the top management. But let's go back to the planning. The planning is kind of where you look deeper into the company of what is going on, how much energy they are using, where they are using it, which is a significant energy users. And it could very well be compressed air, because if I look into the definition of what is a significant energy use and read the standard ISO 50001, I will see that significant energy use is energy use at accounting for substantial energy consumption and or offering considerable potential for energy performance improvement. And I think in very many companies, compressed air is a candidate that live up to both definitions. It consumes a lot of energy, and quite often we see potential for energy performance improvement. So also, what is driving it? Of course, production will probably drive a compressed air system up and down depending on how much you produce, but also weather, if you are dealing with centrifugal compressors, will influence the energy consumption. And who is influencing its use could very well be staff, the operators of the machine, the end users, the operators of the compressors. And do we need to have an energy audit? I would say yes. Maybe they know very well already what they are doing and where they are consuming the energy. System optimization. You should ask yourself, will it make sense to look at the end use when it comes to compressed air? And for sure, yes. End use should be actually the first thing you should investigate. And then you should work backward, upstream, through the pipe system, the treatment equipment, the compressors, and how you control the compressors. Because if you can reduce your leaks, for sure you can also reduce the number of hours you need to operate your compressors, or the number of compressors you need to operate. Should we develop a baseline and indicators? Yes. Also, again, it depends on the size of plant, how much you will develop. But yes, you should develop a baseline and indicators. And then we set objectives and targets, and then we create an action plan. It was a very short introduction to what an energy management system is. I will skip to the next slide and say, when you have selected the SEUs, it could very well be, again, compressed air, or it could be the steam boiler system, it could be the refrigeration system in a food company. Then reporting requirements can be specified. You need to look into what meters and measurements are required to deliver these reports or this information, and how much can be achieved with existing instruments. You should decide if you go manual or automated. List what new instruments are required, and each new instrument should, of course, be able to justify its cost, and don't forget the installation costs. Electricity and liquid flow meters can be of very good value, because they are comparatively cheap to install. Gas flow meters tend to be more expensive if you want to measure on steam and compressed air, but it will pay back for sure if you do this list and do it the right way. The sample measurement plan could look like this. I just brought into this plan refrigeration, which is where we want the ideal measurement could be flow rate, supply and return temperature, and electrical load. And we look into what existing instrument we have already. And the requirement will be chilled water flow meter, and it is simply because we want to calculate the performance indicator for a refrigeration plant, the so-called COP, coefficient of performance. The next one is compressed air. Maybe we will say that ideal measurement is electrical load and compressed air flow. Let's say we have already flow meter, but we need the electrical meter. And what we need to measure here is specific energy consumption as a key performance indicator. It could also be a way around where we have the electrical meters, but need flow meters and pressure profile in the system, or we maybe require all to get the data we would like to see. Also include instruments which measure the critical operating parameters. As I said, I called it before drivers. It could be relative humidity, temperature, things like that. So next slide, I will skip to how you change the company culture for energy savings. An energy management system can indeed help to implement a new culture. We should start with a review of compressed air system, make the baseline, start with a project where you are sure of success, pick a few low-hanging fruits, tell about the success to everybody in a company, also the subcontractors. We need the performance indicators. And remember, when we are dealing with compressed air, we need maybe more than one performance indicator. we can actually produce a compressed air in a very efficient way, and we will see that reflected in kilowatt hour per normal meter cube. But another performance indicator could also be compressed air or electricity go to compressed air per ton of production per week or per month. And the reason for that is the red text here. Note that you can produce compressed air efficiently, and then you can waste half of it in leaks, pressure drops, and inappropriate use. Train the staff in operational control. Tell them that compressed air is expensive, and we need to consume as little as possible. Give access to data, measuring equipment. Everybody wants to do a good job, but they need the right tool. And implement maintenance routine when it comes to leak, filters, cooling, drains where needed. What is benefits of such a culture? It's, of course, obviously lower energy consumption, longer service life of compressors and other equipment, fewer production stops, higher quality of the production, and proud employees who get recognition for their efforts, and savings also in investments. There's a good performance history from compressed air system, including pressure and flow profiles, and thus a new compressor capacity is not purchased if the company does not really need it. We'll skip to a few, what I say, compressed air classics. The next few slides are pictures about what inappropriate use, what means by inappropriate use of compressed air. Here you see an ordinary fan that is producing some combustion air to a boiler system. And this wire you can see going to the bearings is actually compressed air that is an open pipe that blow compressed air down to the shaft and the bearings to cool down the bearings and the fan system. This is not the way you should do it, and it is an extremely expensive way to cool down bearings. I will recommend that you fix the bearings instead. The next one is also one of my favorite. We are here in a cement factory, and to the right you see the silos and the trucks where they load the cement. And obviously there are some problems with the loading system because spillage, the cement does not only go inside the tank, it also put a heavy layer of dust on the top. And here you can see inappropriate use of compressed air to clean the truck before he leaves the company. It's a waste of compressed air, it's a waste of cement, and it is not exactly healthy for the environment, as I will say, because cement dust is not healthy to inhale. Next slide is just to give you a quick overview of a centrifugal compressor, how it works, just to keep you involved in the next few slides. You see the control center, we have the inlet guide vane, we have different stages in the compressor, and after each stage we will have a drain where we have to drain out water from the compressed air. And then we have the bypass valve or the blow-off valve that will protect the centrifugal compressor to go into what we call surge mode. I will show a few pictures about these condensate drains, also another compressed air classic where you can save some energy, because what I see very often is completely open drains where they drain out the water from the intercoolers and aftercoolers, but not only the water, also a lot of compressed air. It is not the way to do it. You should, of course, do it like this, where we have the so-called zero loss drains. And I can also, on top of that, tell you that in this system, we collected the water and sent it pumped it to a cooling tower later on. It will save water resources and also treatment of water for cooling purposes. I finish my presentation with few slides what Enersize is doing, where our core business is, of course, measurement and data acquisition on compressed air system. And we develop analysis methods and software. And this is one of the things we can do. You get a lot of data. We can handle a lot of data, but we need to get an nice overview of what is going on. And this will be the next slide. That system I'm particularly proud of to show you, where we organize cloud-based data, the big data, into different operation modes in colors, and the whole plant profile is visualized in real time, actually. And you can see here, actually, if you need around 100 meter cube per minute, you should operate in the dark blue mode rather than in the light brown mode. And saving potential is obviously around 25% as you go from key performance indicator 0.12 up to, let's say, 0.16. Also, we have the next slide. We have real computer simulations of different operation modes. And you can see this solid line in the bottom here is simulation of the data where we can find savings and see where you operate and where you should be operating, or we can see the development when you move closer to the simulation lines, the solid lines. Finally, I will see, this is a picture I very often see in my job, centrifugal compressor running. If you look at the panel, the control panel, you will see that the inlet valve is 28% open and the bypass valve is 50%. It means that we are wasting a lot of compressed air through the bypass valve. And this is also something we can find how much it is and what is the potential. Again, we have something similar of our simulations. Let's say you operate around 340 meter cube per minute, and you can see the difference between these two clouds of data. And it could very well be, the difference could very well be that up here we operate compressors with a few compressors that is operate with the blow-off valve open, and here we have a better load sharing. This is important, and we need equipment and monitoring systems to see these things. So I must say, make a calculation, implement your energy management system, and look into your compressed air system. You will probably see that most plants can improve the energy efficiency with 5, 10, 15, maybe 20, or even more with very low investments, or at least investments that pay back. I will say thank you for your attention, and I found this picture in one of my companies where I did some consultancy. Do not use compressed air for body cleaning. It's dangerous and it's a waste of compressed air. So I will say thank you, and I will hand over the presentation to Pascal.
Thank you, Bo, for your presentation. Yeah, I think the way you guys visualize data is very, very exciting to see how you do that, and how that gives new insight in. Sometimes you should just have graphs that look like a green field of grass or something like that, but in this way it's much more clear what's really going on. I will pull up my presentation. Compressed air monitoring, no time to waste. I always say, well, the sooner you start with compressed air monitoring and measurement, well, the more money you can identify, the more savings you can realize. And also more important, you can contribute as soon as possible to saving our planet for future generations. So why measure, why monitor? Many reasons, Bo, you already pointed out a lot of this. Predictive maintenance, you can use the data if you visualize in the right way for condition monitoring, for leakage management. It can be used to make founded investment decisions. Very important to monitor efficiency of compressors and also production equipment to know where you're at. If you have data over like a 2-week period or even a year period, you know your baseline, so you know where you should be or where you should work towards. And of course, the ISO 50001 compliance. The next 20 minutes, I will show you a couple of examples of the benefits of compressed air monitoring. So in the first example, I will address predictive maintenance. In the second one, I will show you how you can use flow data to back up investment decisions. And in the third one, I will show you the importance of efficiency monitoring. But first, some basic facts for anyone that's here that's new to compressed air. Maybe you didn't know yet, but compressed air, if you look at the total cost of a compressed air system over 10 years, then the biggest part of the pie is actually energy costs. So equipment is just a fraction. Maintenance can be important in some countries where labor is maybe a little bit more expensive, and it varies per type of compressor. But in general, it's altogether just 25% of your 10-year lifespan costs. So energy is really where you should focus at. Now, where does all this energy go to, what you put into the compressor? A lot of the energy you put into the compressor is actually converted into heat, and only 15% comes out approximately in the form of compressed air, which is then entering the pipe network, and what you then will see is that only 50% of that part is used usefully, and 50% is in general wasted by leaks, by artificial demand, by inappropriate use of compressed air, like cleaning your truck or swiping the floor, etc., or by cooling bearings, as Bo showed also. So what can you do about this? Well, there are various ways to save air, and the most obvious one to start with normally is to reduce leaks. If you're reducing leaks, you're also changing the demand profile, so you also have to look at the control system and the efficiency at the same time, which I will show you in the third example. Reducing the pressure is always good. Lower pressure means lower energy costs. Another thing to look at is, for example, receiver tanks. With a large buffer, a large receiver tank, you can shave off peak loads of your compressed air supply, and that can help to, for example, reduce blow-off of compressors. But now let's go to the first example case, which is predictive maintenance on dust collectors. Well, dust collectors are used in many industrial sites, basically to collect dust from processes. And in those dust collectors, there will be filters which are typically cleaned out with a shock of compressed air, sort of shock wave. These dust collectors have very common issues, like the membrane valves they're using to create those pulses of compressed air. They tend to leak over time. There is a rubber seal inside, which eventually will start to crack. But in a lot of cases, you don't know which one leaks when, and when to repair it. So often this is neglected for too long time. In some cases, it's hard to access, and there's no time for inspection because it might be in a sort of tower-shaped construction, or it might be on the roof of a building. But if that happens, and like for example, a couple of these valves start to leak, they will probably cause a lot of air demand and maybe also some pressure problems in equipment nearby. So the solution to this is actually measure flow in the main supply to the dust collector, and then connect that to a central monitoring system and put some alarms on it. And in that way, you will be ahead of the problem, or you will at least be on the problem when it occurs, and instead of let it go for months or even years. So we had a case a couple of years ago in a steel plant, which I will show you. So here you see these dust collector equipment, these towers. And in this case, they had about 1,000 of these bag filters, which were cleaned out with 1 pulse per minute. And by design, it was specified that there should be an air consumption between 750 and 850 cubic meter an hour on average. So what they did is they installed a flow meter for a temporary audit, and they found out that the air consumption was much higher than specified. It was almost twice in some cases. And if they look more closely into these back filters, they also saw that a lot of these filters were not cleaned properly, because if the valve leaks, there is no air shock anymore. And of course, the root cause, the membrane valves were broken. So they identified that there could be savings, between around 17,000 and 20,000 euro a year. Well, you can buy a lot of those valves for that money. So let's take a look at the data. So here you see the before period and the after period. So you can clearly see that after repairs, that the air consumption went down significantly. And here is some saving calculations. So they had a specific power at that moment of the compressors. In this case, it's not in kilowatt per cube per minute, but in watt hour per cubic meter. So this was a way for them to calculate the approximate costs of compressed air per cubic meter. And then they could calculate the reduction at 8,000 hours of operation and 5,000 hours of operation. And you see these are significant amounts. So after this initial audit and initial repairs, they decided to implement this, to take a couple of permanent corrective actions. So they implemented a permanent condition monitoring system, and they tied it into the PLC or SCADA system that monitored the entire plant, including those filter towers. They got automatic alerts on excessive usage. And very important, they also implemented the maintenance procedures, because you can get an alarm, but you still have to act on it. And thanks to committed maintenance people, they were able to maintain that savings level. In the next example, I'm going to talk about how you can use flow meters to generate data to make investment decisions. And in this example, management of a company needed to be basically convinced that it would be a good idea to invest in some air nozzles. Let me talk a little bit about air nozzles. Those nozzles are based on the Venturi effect, which Mr. Venturi here on this picture, Giovanni Battista Venturi. He was an Italian scientist, and he was the first one that described this principle. And basically, there are many different designs of these nozzles. They're not always nozzle shaped. Sometimes they have different ways to create the same trick. But the basic principle is that a small stream of compressed air drags along ambient air, and by creating a lower pressure. And in this way, you can realize a reduction of approximately 35% compared to an open blow. Well, a lot of people think, well, this is too good to be true, so convince me with some data. And that's where the flow meters come into play. So with flow measurement, you can you can measure the air consumption actually of these potential new investments. You can compare them to the existing situation, analyze results, and then calculate the investment up front. And it's also a good way to negotiate with the nozzle suppliers, because there are differences in designs, there are differences in shapes. So you can really calculate the return on investment versus the capital investment you need to do. So how does it look? Well, you need a few components. You need a flow meter, obviously, and one that measures also pressure and temperature. And you will need a pressure regulator. And you need one of the people that is operating the production equipment, because it's important also to look at the quality of the new process. Is it still up to the quality standards of the thing you want to achieve in production? And then basically it's connecting the air nozzle instead of the existing open blow, and maybe another one, and basically compare those, and also look at different pressures. If you feed it with lower pressure air, it might do the same job as good, or maybe even better. After you have collected some data, you can graph it, which I will show in the next slide, and then you can start to compare it. And this is an actual case where they used an engineered nozzle. There were 5 nozzles in a row to replace 5 open blow pipes. And they also played with 3 open blowpipes, as you can see in this picture, which didn't really make a difference in the air consumption, which means actually that your supply pressure is probably, or the size of the supply line is limiting the flow. And then on the left, you see the lowest graph is generated by this new engineered nozzle. So that is about 50% reduction in, so not 70, which could be reached maybe, but 50%. This was used to blow off chips from wheel rims, and they were able, by investing in these nozzles, to save around 9,000 a year. Third example, this one I will talk about monitoring efficiency. Some large plants, they start very enthusiastic in repairing the leaks, and this results in a dramatic change in consumption. But hey, then the savings are not as expected, you know, if you look at the simple rules of thumb. So why is that? Well, the reason behind this is as soon as you start to change and to play around with the air demand, you're also shifting on the curve of the optimum curve of efficiency. And Bo already pointed it out in some of his very cool graphs. So what happens basically is in the end, when you have reduced all these leaks, the compressor may be oversized compared to the demand. Or the combination of compressors might not be optimal. In the case of centrifugal machines, they will probably start to blow off the air which you have saved downstream. But the problem with it is to predict this is sometimes pretty hard, because the overall efficiency of everything combined, when there is a master control already in place, sometimes you don't know exactly the algorithm which is running into this master controller. So it's sometimes a little bit complex to predict. So that is why it's so important to measure both airflow and electricity consumption at the same time, and to make basically live graphs of the efficiency curve. So what actions to take then if you have saved that, if you have saved and repaired all those leaks? Well, then you should probably contact a consultant, for example, Bo, or people from Enersize, or maybe you have a very, very clever guy inside of your plant, and then you should start to change the control settings. Or you might want to add another smaller compressor, or run the compressors in a different combination to get the efficiency at the optimum level. And I also have seen cases where a booster compressor, including a very large receiver tank, was installed as a sort of air battery. So then the receiver tank air was used basically to absorb peak demands, and that was also a very clever way to eliminate blow off in the centrifugal machines. So how does it look? Typically, it will look like this. So you have kW meters or amp meters on the compressors. You will have flow meters at the demand side, which can be in the main header. But you can also look at individual compressors to monitor the efficiency of an individual unit. Yeah, we already addressed it and also Bo in the previous presentation how to visualize data, and I want to show you another way to do it. That's called a histogram, which is basically it comes from statistics. You basically look at the occurrence of flows, and then you look at the actual flow value itself. So on the x-axis here you see the flow, and on the y-axis you see the occurrence. And the cool thing about this is that you have like a lot of data over like a month or a year. You can still plot it in one simple graph like this. And this is a way to compare, for example, patterns. If you would have two identical machines running similar products, if you would plot a histogram of those two machines, and you will find in one machine a big spike at some point, that might indicate a leaking valve, or that might indicate that something has been replaced by a less efficient valve or something like that. So here's another histogram, and this is basically from a factory, by the way. So then in the first histogram, go back to the first one, you will see a lot of air on the low side. There's a lot of occurrences, and there's less basically flow on the high side. So in this case, this was in summer when there was less production. And then on the next slide, you will see that the company is in full production, and they probably also repaired some leaks. And then you see the sweet spot is clearly pointed out, where the most air and what's the most dominant air consumption of this plant. Before I go to the conclusions, I have some remaining tips. If you walk around in a plant, look for bad practices like open blows, homemade nozzles, homemade air brooms. And you could also ask for the accident report if there any. It's maybe a little bit nasty topic, but if there's any compressed air related accidents, that could also indicate that there is misuse of compressed air, unsafe use of compressed air, and also probably energy waste. So, and there's a very simple solution to all this. Just give them a nice broom to clean the floor instead of using an air broom. So, to conclude this presentation, consumption data is key for predictive maintenance. Use flow measurement or measurement in general to help make founded investment decisions. Efficiency monitoring is key because if you reduce demand, the efficiency could be affected. And in this way, you can maximize savings results. I showed you a tip how to visualize data in a histogram, because then you can see changes at once. And start now, as savings will accumulate over time. So the sooner you start, the more energy you can save. So let's go to the questions and answers part. I will open chat to see if there's already a question. And otherwise, I have a question for Bo to start with. Tell us maybe a short story about a extreme savings case you entered, because you traveled all the world, so you might have a nice story to share.
Yes, I have a very good story actually some years ago from a kind of an oil refinery, palm oil refinery system company, where we started to look into the compressed air system. We equipped it with flow meters and made a pressure profile and stuff like that, and started to look for leaks in the system, and the system actually looked very nice when you just walk in and check the system. But actually, it was there were very many leaks when we started to investigate. There were a lot of inappropriate use of compressed air. We changed from agitation in vessels from compressed air to high pressure blowers instead, just to give you one example. They started a leak maintenance program. We brought a variable speed drive compressor back into operation that was damaged, and did the good settings on the compressed air systems. And I must say, this the reason why we could do all this was because top management, they were extremely committed to save energy. And 1 year later, we had a long-term cooperation with this company. 1 year later, the energy consumption for compressed air was 58% lower. I repeat, 58% lower than it was when we started. And the payback time, I think it was maybe less than half a year. So that's a story I would like very much to share with you. That's not normal what I see. I see normal saving potentials in the region of everything from 10% with well-maintained systems up to 30-40%, because it's not it's easy to get compressed air out of a system, but it's more difficult to operate your compressed air system the efficient way. And this is why we need a monitoring system. We need pressure meters, flow meters, electricity or power meters or amp meters, and we need a nice way to look at all these data. And this is why I like this graphical presentation so much. Maybe I could just add one thing, because we get more and more computer power. We get internet. and we can handle more and more data, but we are how to say still human beings. So with all this data, we also need a better way to look into all these data, and this is where I think you need simulations, and you need a nice way to present all your data. I hope this gave you the answer you are looking for. I turn back to Pascal
for answering my question. There's a couple more coming into the chat right now. So one is what is the simplest type of flow meter with lowest maintenance costs? That's a good one, actually. Well, the simplest type, I would say, is still, and also the best technology for compressed air is still a thermal mass. And why is that? Because the measurement range of the flow meter is very large. So you can measure both very low consumption and high consumption with the same meter. There are also other technologies used, like, for example, vortex meters, differential pressure. And all these technologies, they have different features and benefits. Differential pressure and vortex based typically are used for more harsh environments. So they last basically longer in harsh environments. They can handle much more high temperature and water. So less maintenance. While thermal mass flow sensors, if they are polluted, they need to be cleaned a little bit more often. On the other hand, sometimes a flow meter, if it's just for leakage indication, if it's a little bit just used as a trend, you can also use it sometimes a simpler flow meter than if you use a flow meter which is used for calculating exactly what the efficiency is. So you also have to ask yourself, what is the final purpose of the flow meter you're going to choose. But I have a separate presentation on the comparison between different technologies, which I will be happy to share with Mr. Yafararvi, who shared this, who sent it in this question. Before I go back to Bo, I will answer a second question by Hakan Yigitas. That's about an example in automotive industry, and that made me think of a visit I had earlier this year in a plant in the USA where they used argon. It's not about compressed air in this case; it's about argon welding gas, and they were spending around $165,000 on argon each year, coming from a liquefied argon storage tank. And they purchased one flow meter from us, so roughly $1,500, to measure it. And guess what? They found out that 50% of the argon was being wasted. So that was around $80,000 a year waste identified. And this was because all the welding robots, the hoses were like 25 years old to those robots. So there was a lot of leaking in those hoses, in the couplings. So in automotive industry, you can look much broader than only compressed air. You can also look at the welding gas they're using. It's a very interesting savings case with a very quick return on investment. So I will go back to Bo, because there's a question coming in. If you look at screw compressors installed in a hot environment, in that case, how can you increase efficiency of the compressor? I will go.
For the question, we have to say that basically there's not much you can do if you and the influence on screw type compressors is not very huge when it comes to screw type compressors. It has a much higher influence when we talk about centrifugal compressors. But when when we let's say have a production in Asia where you have a high temperature and high humidity, you simply have to accept this. I'm from Denmark, where we have much colder environment, especially during winter time. And this we can see, especially on centrifugal compressors, that the efficiency of the performance is better during the winter time. there's not much you can do about it. Of course, you can put your compressor in a place where you can provide it with best cooling. I have sometimes seen very small and narrow compressed air rooms where the compressors are very much close to each other, and where the cooling air blow from one compressor blows directly into the inlet of another compressor, and these kind of things can be changed by better design of your compressed air station. But there's not much you can do if you are in Asia. You have to accept your high temperature and high humidity also, and also you have quite often to upgrade your, let's say, refrigerant dryer to a bigger size because of these conditions. So provide the compressors you have with the best possible cooling. I have also sometimes been asked the question, will it make sense to cool down the air before it enters into the compressors? And I will say probably not, unless you have some energy free of cost, some cooling available free of cost, because it will also cost you something to cool down the air from an energy point of view. So do a good design of your compressed air system, do good maintenance, and try to keep the temperature in your compressed air station as low as possible. This is that would be my recommendation to you. Thank you.
We finalize this webinar. Also for you, Bo, they are about pressure loss, how to design your system to keep the velocities as low as possible, and what do you recommend for that, and what is an acceptable pressure drop between the compressor and the last point of use. So I will switch once more back to you before finalizing the webinar.
Well, because I lost sound for a short while, but I understand. Please, what is the pipe velocity you recommend to minimize pressure drop? I think that was the question, and I will say in the main pipe system is around. We recommend something not higher than 6 meters per second. And when we are dealing with a smaller pipe system, for example, from the main to production machinery, we can accept up to 15 meters per second. So if you can operate preferably lower in your pipe system with these velocities, then you are almost on the safe side that you will have a pressure drop less than 0.1 bar in the pipe system. But remember, on top of that, you may see also pressure drops in the dryer equipment and in filters and other places. Allow me to say that where I see the highest pressure drops is quite often from the main down to some production machinery where they have connected a two small diameter plastic hose or rubber hose or something like that, and so maybe you provide, let's say, 7 bar on the main, and then when it goes through the last maybe 10 meter of rubber or plastic hose, then you drop with 1 bar. And most companies, they will just say, okay, we need the certain pressure here, so we have to operate the compressors on a higher pressure, and that will cost you a lot of energy. As a thumb of rule for screw type compressors, between 6 to 8% per bar you increase the pressure. So but check your velocities. Again, I repeat, in main 6 meters per second, and in the end-use pipes going from main to the machinery, we can accept up to 15. But pressure drop is also a place where you quite often can find saving potential. Thank you.
Thank you so much for answering these questions. There are a couple of more, but we have to get back to this after the webinar. Everybody, thank you so much for also attending today. I hope you liked the topic. After this webinar, there will be a short questionnaire where you can also drop suggestions for new topics. So feel free to give us your ideas. And a recording of this webinar will also be available soon after this, so you can share it with your colleagues or check it out again to maybe learn again something which you missed during the webinar. So thank you, and have a great day. Thank you.